So why do I need all these holders and adapters and collets? Why can't I just take my drill chuck and put my end mill in? Doesn't that make it easier? This is the second in a series of basics videos that I'm doing where I take questions that I've actually received and try to answer them. Really basic stuff that a lot of us already know, but a lot of us had to learn at some point, and the best way to learn is to ask questions. There are also questions that the big machine channels out there just kind of gloss over and kind of expect you to know when you're watching their content. And that's nothing on them. It's just when you're making machining videos, if you already know something, you kind of expect the people who are watching to know it too, but not always. Especially in amateur home shop machining with mini mills and mini lathes. So in the last basics video I talked about tool holders and collets and drawbars and the different types of tapers. I got a question on Instagram from one of my subscribers, and it was a very basic question, but it's also a question that I remember I had at one point. I just got a drill press and I thought, well, why can't I just put an end mill in there and get an XY table and do some basic milling? But it's not something that's just been said over and over, you know, don't put an end mill in a chuck. There also are really good reasons why you don't want to. There's also one situation where it's not that big of a deal. So as I said before, this is all from the perspective of an amateur home shop type of machinist. If there's any actual machinists out there or other people who have knowledge of this sort of material, please comment below if you have anything to add, or if I missed something, or if I say something wrong. Please comment below, let me know. And as always, if you like this sort of content, please leave me a thumbs up. That lets me know you like it, and it also lets YouTube know you like it, which means other people will see it. So as we go through this video, you're going to notice that the most common theme that keeps coming up is rigidity and stability. And let's start at the top of this particular drill chuck shank and talk about some of the reasons before we even get to the actual drill chuck itself. Now, a tapered shaft with a tang on it is great for drilling because all the forces are pushing back up. So the main axial force of the drilling action is pushing the chuck farther up into the taper, and the rotational force is being taken up by the taper as well as the tang. So that's a perfect shank for drilling. It's not such a perfect shape for milling, because milling introduces side forces and down forces. And side force is exactly what it says. It's the movement side to side. If you've ever tried to get anything tapered out of a taper, you know that one of the ways you do that is to wiggle it. And by wiggling it, it gets freer and freer. So side force is not good. The other force that can happen when you're milling is there can be a pulling force. When you are skating across a piece of metal, this cutter wants to suck down in that metal, and there has to be something that resists that. And if all you have resisting that is the friction of the taper, it's not enough, and eventually that's going to pull that out or loosen it just enough to where it'll start to vibrate, which introduces the other force that I just talked about, and that'll work itself out and it'll get pulled out of the spindle. So at this point, if you watch my other video, you might be saying, well, what if I use a drawbar? What if I suck this taper up into the spindle, and therefore you don't have as much possibility of the pulling action or the shaking action? Well, then we get into the chuck. So chucks are normally held in also with a taper, a Jacob's taper in many cases. You see a Jacob's taper here. There is just a taper in there, and this shank is fitted into that taper. Same thing applies to this taper as applies to this taper. Even though you have the screwed in top taper, not the same on the bottom. So you have the same sort of pulling action, side to side action. Well, then you might say, well, what if I have a screw-in chuck, such as this one? And I'll say, okay, let's move on to the next thing. These tapers are different size. This one's a Morse 2 and this one's a Morse 3, but where the spindle stops is about right here. This end mill holder overhangs about an inch less than this chuck. Overhang causes rigidity issues. Even though you can't bend this by hand, the forces in milling could possibly bend this enough, just enough, it's not a lot, just enough to introduce chatter, which gives you bad finish, it eats up your end mills, and it's just overall bad. It's not very rigid. You want to minimize that overhang as much as possible. But let's say you're like, I can deal with the rigidity issue. I can, reduce the distance to the workpiece as much as possible. chuck up the end mill in there, all the way up in there. Let's say you want to go that route. So then we have this problem. This is the inside of a cheap but typical chuck. It does not have a split ring, which is I think a little unusual, and I was hoping to be able to get the jaws out, but I'm not sure how this one comes apart any farther, so I'm not going to mess with it, but I think you'll get the idea. As you turn this collar, which is turned by the outer sheath, which is a really tight fit on there, as you turn this collar, the jaws retract as well as extend, and you can kind of see that here. Notice something about these jaws. Those teeth, first of all, very fragile. The reason this one is apart, this is an old Jacobs chuck, is because the teeth were broken on some of them. Somebody had tried to remove the outer ring with the teeth in the wrong position, and that caused some cracked teeth. Notice these jaws can rotate. They have a little bit of slop up and down. They have slop side to side, and they have slop rotationally. And they have fragile teeth. These are a little bit smaller than the Jacobs ones, but the Jacobs ones are just as fragile. And the reason is because these are hardened. The jaws of your drill chuck are hardened, and that will become more important in just a minute. So we have that problem. That's a rigidity problem. I told you there was a theme here. Another problem is the number of teeth. You'll notice on a collet, the end mill, or whatever you put in it, is encapsulated all the way around. When this squeezes together, it closes around it. If one of those teeth gets a little bit loose, or is in a little bit the wrong position, or is ground a little bit off, and by the way, they will have a little bit of run out. Even the best chucks have a little bit of run out. If you put something in there and you've got slop in the teeth, you go to tighten it down, and it is holding it in a way that there's the potential of rigidity problems. Once again, the rigidity issue. Also the fact that, notice how long these jaws are. The jaws on the Jacobs chuck, this is a, what is this? This is the number 34 chuck. This is an older chuck, half-inch chuck. The jaws on it are about 2.5 inches long. Imagine holding something with 3 fingers and you hold on to it like this, and then you go try to screw something in. Do you have more force? Is it less likely to slip than if you hold it like this, up tight against yourself, or like this, even better, which is completely surrounding it? I can pretty much guarantee that you'll have more force doing it this way than you will doing it with 3 fingers doing it this way. So we've almost beat this to death about how drill chucks are not the most rigid things. They're just not designed for that lateral forces. There's one other aspect about drill chucks that I mentioned quickly that is also a problem. The jaws on most of your drill chucks, any good drill chuck, are hardened. Your drill bits, however, are typically, but not always, but typically, for the most part, most drill bits you're going to find are not hard. That's why they get scratches and gouges. That's why these jaws can do that to these. That helps the jaws to actually bite into the chuck and hold it. End mills typically are hard throughout. So when you have a hard surface against a hard surface, they tend to slip. Well, unless they're mirror finishes, and I'll let somebody else explain that. Slipping's bad because once it starts to slip, it comes in and out, ruins your workpiece, and you've wasted your time. Now, having said all this, there is a time when you might want to use an end mill and a drill press. The only instance I can think of where it's not a terrible idea, actually. It gets the job done, and it's cheaper than buying the right tool. And if you know other reasons, of course, to use one, please let me know, but this is the one that I've used before and I can think of. You've drilled a hole and you want to make a counterbore for some reason. You want to go in there and make a flat bottomed counterbore. Well, you can put your end mill in there just after you drilled your hole. Just use the same setup, put your end mill in there, and drill, that's the important part, drill a counterbore. Now, what I normally do in that case is is chuck it all the way in so it bottoms out and tighten it down as hard as I can, and then just drill your counterbore. And that works. It's not a you're not doing a lateral movement, you're just going straight up and down, and you're using the flatness of the end mill to achieve a counterbore instead of having a counterboring bit. Perfectly acceptable. I don't think that there's too many machinists out there who would disagree that that's an acceptable use of an end mill in a drill chuck. So I hope this answers the question in detail, and if anyone else disagrees or has another reason why a drill chuck is bad or another reason why a drill chuck is good, please chime in the comments. As always, I appreciate you watching, and we'll see you next time on we'll do another basics video. I think the next one's going to be on vices. I already had a question on vices, so I think we'll do it on vices. Thanks for watching.